All right, class. I thought I'll start as usual by telling you what happened last time. Not the whole thing, but just the highlights so you can follow what's happening today. The main things I did last time were the notion of an electric field, which is going to be with you from now till the end of the course. And the idea of the electric field is that if you got lots of charges, Q1, Q2, Q3, instead of worrying about the force they exert on each other, you ask yourself, at a generic point where there's nothing, if I put 1 coulomb here, what will it experience? What force will it experience? You compute that. So in your mind, imagine a coulomb, and you find the force due to Q1 may look like that. Q2 may exert a force that way. Q3 could be of opposite sign, so maybe it'll exert a force that way. You add all these vectors, they add up to something. That something is called the electric field at that point. There is nothing there except the electric field. But it's very real because if you put something, something happens to it. Okay? So the electric field is everywhere. The charges are in a few places. Electric field is defined everywhere except right on top of the charges where probably is infinite. Once you know the electric field anywhere, if you put another charge Q, a real charge, it will experience a force equal to Q times E, because electric field was the force you would have had on 1 coulomb, and if you put Q coulombs, it will be Q times C. That's the electric field. So you can imagine computing it for any given distribution of charges, because you know what each one of them does. Then I said there's one nice way to visualize the electric field, which is to draw the field lines. You go to each point, and you ask, if I put a charge here, a positive test charge, which way will it move? Then you follow that thing as it moves, and you get that line, and you get that line, and you get that line. You can draw these lines. The lines give you one piece of information which is very obvious, namely, if you're here, the force is along that line. But I also pointed out to you, you get more than just the direction of the force. You also can understand the strength of the force. The strength of the force is contained in the density of these lines. Now, density has to be defined carefully. It's not like mass per unit volume. It's an area density. That means if you get yourself 1 square meter, meter by meter piece of wood, like a frame, and you hold it there perpendicular to the lines and see how many lines go through. That's called the area density of lines. That, you can see, will fall like 1 over r squared, because if you draw a sphere of radius r, that area is 4 pi r squared, and the same number of lines are going through that as any other sphere. So it will be proportional to 1 over r squared. But so is the electric field proportional to 1 over r squared. And I said, let us agree that we will draw 1 over epsilon 0 lines per coulomb. This is not a necessity. It's just a convenience. It's like saying I want to measure distances in inches and centimeters for daily life. You can measure them in parsecs or angstroms, but you'll be dealing with nasty numbers. So it's a convenience, and the convenience here is let's pick 1 over epsilon 0 lines per coulomb. You'll see the advantage of that, because if you ask what's the density of lines here on a sphere of radius r, if there is charge Q at the center, I got that many lines, and the area of the sphere is 4 pi r squared. So the density of lines per unit area, you see, is precisely equal in magnitude to the electric field at that point. If you had not drawn 1 over epsilon 0, but maybe 5 over epsilon 0 lines, then the line density will be 5 times the electric field. It will still represent the electric field, but we don't want it to simply represent it. We want it to be the electric field. It makes it easier. Okay. Then I said, let's take a slightly more complicated situation, 2 charges. This is called a dipole, 1 pole and another pole. And you can draw the field lines here. You can see if you put a test charge, it'll run away from the plus to the minus. If you leave it somewhere here, it'll go like that and loop around and come back. And you can calculate them. This is no longer guesswork. If you had enough time, I hope you all agree, you can go to any point you like and find the force of attraction due to this one, the force of repulsion due to that one, add them up, and you will get an arrow in that direction. So one can draw these lines, and the lines tell you a story. All right. Then I said, let us find the field in an analytic expression due to the dipole. Yep?
Quick question about the dipole. If you put a test particle going in the positive direction on the x-axis, would it also loop around?
No. She's got a good point. If you put somebody here, it will never loop around. Can you see why? Because as it goes further away, this is trying to pull it back, but it's always going to be closer to this guy. So it's never going to come back. So this line will go like that, and this line will go like this. But anything else at any other angle will loop around and come back. All right. Now the field strength, if you want to calculate it, you can use the formula for E due to this one and E due to that one and add them, and I did that for you. I don't want to go into the details, but I remind you, in all cases, the electric field fell like 1 over r cubed. Because the field of each charge goes like 1 over r squared, and if these were on top of each other, they will completely cancel each other. So the reason you have a non-zero field is thanks to A. Therefore, the answer has to contain an A in front of it, at least in the first approximation. But that A, from dimensional analysis, has to come with a 1 over r so that the whole thing has the same dimension as before. That's why you get A over r cubed. That A times Q times 2 and so on, that became the dipole moment. That was true here. We verified that's true here. Later on, we'll verify it everywhere because there are easier ways to calculate than what I'm using. Then I said, let's look at, forget about the field due to charges. Let's look at what charges do when you put them in a field. So I took 2 examples. One was a very simple example. These are 2 parallel plates. Okay, they are not 2 lines. They are plates coming out of the blackboard. They're filled with charge, and this has got plus charge on it. It's got minus charge on it. And therefore, the electric field will look like this, right? Because if you leave a test charge, it'll go away from the positive towards the negative. Then I said, suppose I release a particle here with some velocity v naught, what will it do? You can see that the force on this guy is going to be Q times E. E is pointing down. If you divide by the mass, that's the acceleration, also pointing down, and it's constant. So that's like a particle in a gravitational field, except G is replaced by this number. So it will just curve like that, and you can calculate the trajectory. Final thing I did was, what happens when you put a dipole in a uniform field? Here is where I think I was rushing near the end, and even I couldn't read my stuff in the corner. So I will go over that. If there's something you didn't follow, then I will be happy to repeat that part for you. But you should understand what the question is. There is an electric field which is pointing like this, as if you had 2 plates here, okay? Plus charges here, minus charges there. They're producing a constant electric field in the horizontal direction. In that environment, I take an electric dipole whose minus charge and plus charge, plus Q and minus Q, happen to be oriented like that. Question is, what will happen to this guy? If you want, you can imagine that is a little massless stick, and one end you glue Q coulombs, other end you glue minus Q coulombs, and you let it there. What will it do? First of all, it won't feel any net force because the force in this direction is Q times E, and the force that direction is also Q times C. If you want, it's minus Q times C, and they cancel. But that doesn't mean it won't react. It'll react because you can all see intuitively it's trying to straighten this guy out and applying a torque like that. You follow that? That's what it will do. And the way to find the torque is the product of the force and the distance between the point of rotation and the force and the sine of the angle between them. That is to say, sine of this angle. What the sine of the angle does is to take the component of the force perpendicular to this axis. Because if you resolve the force into that part and that part, this part is no good for rotation. That's going to stretch the dipole along its own length. It's a perpendicular part that's going to rotate something. So you get that times sine theta. That you can write now as a vector equation, P cross E. Because P is equal to, I'm sorry, I need a 2 here. I forgot the 2 because this charge will have a torque and that charge will have a torque, and the two torques are additive. They're both going the same way. Then 2q times A is P, and this is E, and the sine theta comes from the cross product. I'm assuming all of you know about the cross product. Okay. Final thing I did, which is if you have a force, you can associate it with that force a potential energy. Again, this is something you must have seen last time, but I will remind you. As long as it's not a frictional force, you can say the force is connected to potential energy in this following fashion. Or the potential energy at x minus potential energy at some starting point x naught minus x is the integral of the force from x naught to x. This is the relation between the force as the derivative of the potential, and the potential is the integral of the force. For example, for a spring, U is 1/2 kx squared, and F is equal to minus kx. And if you go to this one, it will tell you U of x naught minus U of x is equal to minus kx dx from x naught to x. So that gives you kx naught squared over 2 minus kx squared over 2. And by comparison, you can see U of x is equal to 1/2 kx squared. Actually, this is not the unique answer. Do you know why? Given this formula, can I immediately say this guy corresponds to that, this one corresponds to that one? Is there some latitude here? Yep.
You can always add in a constant.
You can add a constant to both, because if I said that certainly works. If I add 92 to both, it still works, because the 92 extra doesn't matter when you take the difference. So it's conventional to simply pick the constant so that the formula looks simple. Coming to our expression, if you had a torque, which is Pe sine theta, you can ask, that's the torque. It's minus because it's trying to reduce the angle theta. You can ask what u leads to that, and you can see it's minus Pe cosine theta. See that? Take the minus u and take the derivative, you'll get the torque. But if you got two vectors P and E and you see the cos theta, I hope you guys know that you can write it as a dot product. So that's the end of what I did last time. Okay? The potential energy is proportional to the dot product of P with E. The torque is equal to the cross product of P with E. And what this Pe cos theta means, if you plot it as a function of angle, it will look like this. This is pi, and this is 0. That means it likes to sit here, and if you deviate a little bit and let it go there, it'll rattle back and forth, just like a mass spring system. In fact, you can very easily show near the bottom of the well, the potential energy is proportional to theta squared. That's because cos theta can be written as 1 minus theta squared over 2 plus theta to the 4th over 4 factorial, etc. For small angles, if you just keep that term, you will find it looks like this. Not very different from u equals kx squared. So what x does with forces, theta does with rotations. All right, so this is what we did last time. Now I'm going to do the new stuff. So new stuff is going to give you, I think it's useful because it tells you the level at which you should be able to do calculations. So here's a typical problem. You have an infinite line of charge, of which I will show that part, and somebody has sprinkled on it lambda coulombs per meter. So it is not a discrete set of charges. It's assumed to be continuous, and it's everywhere. I'm just showing you a few of them. And if you cut out 1 meter, you'll find there's lambda coulombs there. And you want to compute the electric field you will get due to this distribution everywhere. So you want to go somewhere here and ask, what's the electric field? That's what we're going to do. Okay, let's go here. You'll see why. Now, first of all, you got to have an intuition on which way the electric field will point. Okay, you have a feeling? Yes, it'll point here, this way. Why not like that? Yep. Okay. She said the horizontal parts will cancel. That's correct. Another argument from symmetry is that if anybody can give me a reason why you should tilt to the left, I can say, why don't you use the same argument to say it'll tilt to the right? Because this is an infinitely long wire. And things look the same if you look to the left and if you look to the right. And the field you get should have the same property. If this was a finite wire, I wouldn't say that, because in a finite wire, there can be a tilt somewhere here. But infinite wire, it cannot tilt to the left or to the right, because each point has the same symmetric situation to its right and to its left. In a finite wire, it's not true. Life to the left is different from the life to the right. But for infinite wire, you know it's cannot be biased one way or the other. It's got to go straight up. Secondly, you can find the field here, 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 or anywhere at the same distance. You got to get the same answer. Again, because if you move 2 inches to the right, it doesn't make any difference to an infinite wire. You still got infinite wire on either side. Okay, so we'll pick a typical point and calculate the field, and we know that answer is going to be good throughout that line. So now I take this point here. I want the field here. I'm going to make that my origin. Then I take a piece of wire of length dx. Dx is so small that I can treat it as a point. Now, the dx I've drawn is not a point, but in the end, we're going to make dx arbitrarily small so that it's good enough. It's like a point, and it is at a distance x from the origin, and let's say that distance is a. So let's find the field due to just this guy, this shaded region. Think of a charge. How much charge is sitting here? I hope you all agree the charge sitting in this region is just lambda times dx. That's just a definition. If you got that many coulombs, imagine a test charge of 1 here. Well, it'll push it this way. And the field due to that, I'm going to draw as infinitesimal, so I'm going to call it dE. You can call it E, but dE is to remind you it's a tiny field due to a tiny section dx. Now, that electric field is biased to the left. But for every such section you find here, I'll find a section on the other side that's precisely biased to the right by the same amount. Therefore, the only part that's going to survive due to this guy, combined with this, will be the portion here, which is the horizontal part, which is the vertical part of that force. So let me find the contribution first, only from this one. Then we will add the contribution from this one. For that one, you just find the vertical projection. So how much is that? Remember the Coulomb's law for the electric field is Q over 4 pi epsilon 0 r squared. So this is the Q. That's a 4 pi over epsilon 0. R squared is that distance square, which is x squared plus a squared. That's really like the field of a point charge at that distance. But now this is the magnitude of the electric field vector at this angle, but I want the part along the y direction. So I got to take cosine of that theta. You guys follow that? If you took this vector, this part is dE cosine theta, that part is dE sine theta. But that angle and that angle are equal, and cosine theta for this triangle, you can see, is a divided by a squared plus x squared square root. So this is the electric field in the y direction. I'm going to call it dE in the y direction due to the segment dx. The total electric field is obtained by adding all the dEs or adding all the contributions from all the segments on this line. And that goes from minus infinity to plus infinity. All right, so now it's a matter of just doing this integral. So this gives me lambda a over 4 pi epsilon 0 dx divided by x squared plus a squared to 3 over 2 from minus to plus infinity. Now, I can make life a little easier by saying that this function is an even function of x. That means when you change x to minus x, it doesn't care. Therefore, the contribution from a positive x region is the same as the contribution from a negative x region. That also makes sense in this picture here, because if you look at the field I'm computing, this section and this section give equal contributions in the y direction. But even if you did not know any of that background, as a mathematician, if you see this integral, you would say, hey, put a 0 there and put a 2 here, namely integrate over half the region, because the second half is giving you the same answer. So you double the integral, but cut the region of integration to half. So at this point, you are free to look up a book if it was an exam. Well, maybe not even if it's an exam for at your level. You should be able to do this integral. So integrals have been around from the time of Newton, and the question of an integral is find the area under some graph with this particular functional form. And the answer to any integral is it's that function whose derivative is the integrand. So what you have to do is guess many answers till you get the right one. But people have been guessing for hundreds of years, and there's big tables of integrals with all the integrals you want. But you should still be able to do some integrals from scratch, and I'm going to tell you how to do this one. But before you do the integral, you got to have some idea what the answer is going to look like. I want you to get some feeling for this. Answer depends on what? That's the first question. What's the answer going to depend on? A. You understand? Whatever this is depends only on A, because 0 and infinity are not going to be present as part of the answer. If the lower limit is 5, it can depend on 5, but it doesn't depend on any other thing other than A. Then from dimensional analysis, I got a length squared to the 3 over 2, that's length cubed, and a length on the top. So the whole thing should look like something over length squared. The only length I have is A, so it's going to look like 1 over A squared times a number. Once you got the number, you're done. So I'm going to do all the work now to show you that the number is actually just 1. This number will turn out to be 1, in which case you will find it's lambda over 2 pi epsilon 0 A. Well, let's see how to get the number to be 1. So does anybody know what trick you use to do this integral? This is whatever math, 120 or, yep.
U substitution?
Yes? What substitution?
X squared plus A squared equals U.
That won't help you. Yep.
You use a trigonometric substitution?
Yes, trigonometric substitution. Which one? Okay, look, this is, no, I don't blame you. I know the answer because I've seen it, but if I had to work on it, I'll try for a while before I got it right. The whole idea is we don't like all these 3/2 power here. We want to turn that into something nice. So I'll tell you what the answer is. You can all marvel at how wonderfully it works. So what we're going to do is to introduce an angle theta. nothing to do with the angle in the problem. So that x is equal to tan theta. That means instead of going over all values of x, I'll go with the suitable values of theta. I'm sorry, this would not even be correct dimensionally. X equals a tan theta. You can see that every x that I want, I can get by some choice of theta, because tan theta goes from 0 to infinity when theta goes from 0 to pi over 2. You cannot say x equal a cosine theta, for example. You are doomed. If x is a cosine theta, the biggest x you can get is a, whereas I want this x to go from 0 to infinity. So when you make the change of variables, you got to make sure that for every x you want, there is some theta that will do it. Then the next thing you do, you say dx over d theta is equal to a times derivative of tan to secant squared theta. Then you write that as dx equal to that. What that means is an interval dx is related to an interval d theta by this factor. Therefore, going to that integration here, I'm just doing that part, which is going to be a secant squared theta d theta. Theta goes from 0 to pi over 2. Now let's look downstairs. Downstairs, I got x squared plus a squared. X itself is a tan theta. Therefore, it's a squared times 1 plus tan squared theta. 1 plus tan squared theta happens to be secant squared theta. That to the power 3 over 2, which is what I want, will give me an a cubed secant cubed theta. So what do we get? You can see, as promised, I get a 1 over a squared, and I get integral 1 over secant theta, which is cosine theta, d theta, from 0 to pi over 2. Yes. And integral of cosine is sine theta from pi over 2 to 0. That just happens to be 1. So the final answer is what I gave you here, E. Well, E is a vector. I've just told you the magnitude, but we've all agreed on what the direction is. Direction is away from the wire. So if you like, if I look at this wire from the end, the lines will look like this. If the wire, infinite wire, is coming out of the blackboard towards you, and you look at this way, if you go too close, you'll poke your eyes out. If you look from here, you'll see the lines are going out radially everywhere. The question is, how do the fields get weak? How does it weaken with distance? It weakens like 1 over a. That's a bit of a surprise, right? The field away from the wire doesn't fall like 1 over distance squared, but falls like 1 over distance. The reason is that every individual portion of the wire has a contribution that does fall like 1 over distance squared, but it is an infinite wire. When you add it all up, the net answer goes like 1 over the distance. The field away from a wire falls like the distance from the wire, on the perpendicular distance from the wire, and it's pointing away from the wire. That's it. Okay, so that's one calculation. Then I'm going to do one more, and that's going to be the end of the tough calculations. Second calculation is going to be an infinite sheet. On the infinite sheet, the appropriate quantity is called the charge density, which is coulombs per meter square. That means if you cut out a tiny piece, the charge on it will be sigma times the area of that piece. So that is positive charge everywhere here. And the number of coulombs per unit area is called sigma. So these are standard. Lambda is coulombs per meter. Sigma is used for coulombs per unit area. And the question is, what's going to be the electric field at some point away from that plane? Once again, I think we can all agree that the electric field at some point from the plane will not depend on where in front of the plane you're standing. Are you standing here or are you standing there? It doesn't matter, because it's an infinite plane. If I moved 1 inch, I'll tell you why it won't matter. Okay? If I moved 1 inch and the answer changed, I should get the same change if I didn't move and somebody moved the sheet 1 inch the other way. But when I move an infinite sheet the other way by 1 inch, it looks exactly the same. It's got to produce exactly the same field. So you can always ask, what will happen if I move to the left? The same as what will happen if the sheet moves to the right. The sheet moving to the right looks exactly like the sheet before. The answer won't change. Therefore, the answer won't change for you if you move to the left. If you've got infinite plane below you, as long as you don't change the distance from the plane, you navigate perpendicular to it, no matter where you are, you will get the same answer. Same answer meaning same direction of the field, same magnitude. And that direction has to be perpendicular to the plane. Again, from symmetry reasons. If you tilt it in any one direction, you have no reason to do it. For example, if you tilt it this way, I can take the infinite plane and rotate it, then the tilt will be in some other direction, maybe like that, but the rotated infinite plane looks the same. In other words, if the cos does not change, the effect should not change. So if I can do certain things to the infinite plane that leave it invariant, then I can do the same transformation to the location of the point, and that shouldn't have a different answer. So the plane has a property that when you slide it up and down parallel to itself or twist it and turn it, it looks the same. Therefore, the field pattern should have that property. Therefore, the field has to be the same at all distances from the plane, anywhere on top of the plane. And it's going to point this way, but you can also find out in a minute. By the way, you don't need any of the symmetry arguments. You just do the calculation by brute force. It will have these properties. But it's good to know what to anticipate, because maybe you made a mistake somewhere. It's good to know some broad features. So none of this is needed to calculate. Even in that problem, go ahead and find the electric field, not where I found it, but 2 inches to the right. You'll find the answer looks the same. So those symmetric properties will come out of the wash, but it's good for you to anticipate them. And that's where you should look at the symmetry of the source. For example, the source was a ball of charge. You know, if you rotate the ball, when I'm not looking, if you rotate the ball, it's going to look the same. That means the field pattern should have the property when you rotate it, it looks the same, because the same cos should produce the same effect. Anyway, going to this problem now, let's find the electric field here. Okay, now this is going to be a stretch for me to draw, so I'm going to try, but you will have to go look at some textbook if you want a really nice looking picture, but this is the best I can do. I take a ring of radius r and thickness dr. I take an annulus. And I ask, what will that ring do to this point? So let's take a tiny part of that ring, this guy. Well, for that, you just do what you do with the wire. You draw a line here. It will produce a dE that looks like this. What is its magnitude? Magnitude is just given by Coulomb's law. The Q there is sigma times the tiny area dA. Let's call this dA. dA is a name for a small area. Sigma times dA is a name for a small charge. That charge will produce a force 1 over 4 pi epsilon 0 square of the distance, r square plus a square. Finally, here is where the symmetry comes in. Can you see that for every section here, I can find an opposite section that will cancel everything but the part perpendicular to the plane? So I should only keep this portion of it. Namely, I should take the cosine of that theta. And the cosine of that theta is the distance a, just like in the other problem. A divided by r squared plus a squared to the 1/2. This is now dE. If you want, you can put this following symbol, dE perp, meaning perpendicular to the plane. Yep?
You need to multiply by 2 again, since you're making the symmetry argument and only.
Let's be careful. Her question was, should I multiply by 2 because of this guy here, right? In fact, I should multiply by all kinds of other numbers, because so far I found the field only due to this segment here. I got to add the field due to that and that and that and that and so on, right? What will their contribution be? For every one of them, this factor r squared plus a squared to the 3 over 2 is the same. They all contribute to the same factor. So when I added the shaded region, I'll just get the area of the shaded region. All these dAs, if you add them up, what will I get? It will be sigma over 4 pi epsilon 0. Now you've got to ask yourself, what's the area of an annulus of radius r and thickness dr? So take that annulus, take a pair of scissors, and you cut it, and you stretch it out like that. It's going to look like this. This is dr, and this is 2 pi r. So the area of an annulus is just 2 pi r dr. So sum of all these areas is 2 pi r dr, and then I've got here r squared plus a squared to the 3 over 2. But now, this is the dE due to an annulus of thickness dr. Then I got to integrate over all values of r, but r goes from 0 to infinity. So I have here sigma over 2 epsilon 0 times r dr divided by r squared plus a squared to the 3 over 2, 0 to infinity. Did I miss a pi?
Shouldn't it be sigma over 2 pi?
Oh, that is a 2 pi here,
Okay, yeah. Okay.
2 epsilon 0. So do you understand what I did? I broke the plane into concentric rings, and I took one ring. I'm looking head on at that ring. I took a portion of that ring and see what field it produces. And I know that even though the field due to that is at an angle, the only part that's going to remain is the part perpendicular to the plane, because the counterpart of this one on the other side will produce a similar field with the opposite angle here. That will cancel, so only the part perpendicular will survive. Then I found out that the contribution from every dA had exactly these factors. They all had the same r, they all had the same a. So sum of all the dAs, which is all I have to add, is 2 pi r dr. And that's the contribution from this annulus. Then I still have to look at annulus of every radius. So that's the integral over dr. Yep?
What happened to the A on top, the one that was A over?
Oh, I'm sorry. No, it's there. Thank you. There is an a still here. Yeah, I would have caught that guy in a while, but I'm always happy when you do that. That's correct. Okay, so now, how about this integral? You have any idea what you might do now? Yep.
U substitution?
Right? U substitution is a pretty safe answer, but you got to go a little beyond that.
Substitute r squared plus a squared for u over 2.
Yeah, you can do that in this problem because there's an r on the top. If you didn't have the r, you couldn't do that, but now you can. I'll tell you how it works. First of all, you can always do that tan theta substitution even here. It will always work. The tan theta substitution, if you put it here, it will still work. Okay? You can go home and verify that, but I will do it a different way now. I will say let w equal to r squared. Then dw is equal to 2r dr. So if I come here, I can write it as a sigma over 4 epsilon 0. I borrow 2 top and bottom to make it dw. W also goes from 0 to infinity, but now I get w plus a squared to the 3 over 2. Now this is a simple integral. Dx over x plus some number to some power is x to the n plus 1 over n plus 1, but n is now minus 3 over 2. So you get a sigma over 4 epsilon 0 divided by w plus a squared to the minus half divided by minus 1/2, which is minus 2 on the top, and that goes from infinity to 0. So I'm not going to do this much slower than this. This is the kind of integral either you can see right away, or you can go and work out the detail. This is something you should do. If you have trouble with such integrals, then you should work harder than people who don't have trouble with such integrals, but because you should be able to do x to the n plus 1 over n plus 1 and know that n plus 1 is minus 1/2, and when it comes upstairs, it becomes minus 2. And now if you look at this integral, in the upper limit when omega is infinity, you get 1 over infinity, which is 0. The lower limit when omega is 0, you get 1 over a, and that will cancel the a here, and you will get sigma over 2 epsilon 0. So that's the final answer. So the electric field of this infinite plane, if you look at it from the side, looks like this. It is sigma over 2 epsilon 0. So what do you notice about this one that's interesting? It doesn't fall with distance. No matter how far you go from this infinite plane, the field is the same. Again, each part of it makes a contribution that falls like 1 over distance squared. As you go further and further out, you might think the field should get weaker, right? How could it not get weaker? You're moving away from everything. At least with the line charge, it didn't go weaker like 1 over r squared, but it did get weaker. How can you go further and further from a plane? You are going further away from everybody. How could it not matter? Yes, any ideas? For example, if you go very close to the plane, what happens? If you go really close to the plane, what happens is the field due to any section here looks like this. Therefore, the part that's useful is very small. If you go further away, you get things like that. Maybe it's a little weaker, but the part that's useful, this one, is getting bigger. So by magic, these tendencies cancel in the end. Doesn't depend on distance. Now, unless you do the integral, you will not know it doesn't depend on the distance, because you can give arguments for why it'll get weaker, arguments for why it'll get stronger. The fact that it'll precisely be independent of distance, you have to do the calculation. Yes?
What happens to the negative sign?
Negative sign where here?
Yeah.
Minus 2 is there, but the upper limit is infinity. So the
Okay.
okay, it's, all right. All right, now here's the third problem. And the good news is I'm not going to solve it for you, but I'll tell you what it is. Here's a solid ball of charge. It's got some charge density rho coulombs per meter cubed. So rho is the standard name. You know you use density for mass over volume, and you use the same symbol rho for charge per unit volume. So somebody has assembled a blob of electrical charge, and 1 cubic meter of that has rho coulombs. You want to find the field due to this one. Now, when you do the similar problem in gravitation, it is generally assumed that when you're outside the sphere, the whole sphere acts like a point charge with the entire charge sitting at the center. But you actually have to prove that. That's what took Newton a long time to prove. He knew it was true, but he couldn't prove it. Because for that, you got to be able to do integral calculus. And even today, to find the field due to a sphere using integration is quite difficult. Think about what you have to do. You want to sit somewhere here. First of all, for a sphere, we know the field is going to be radial. It doesn't matter where you pick. Everything looks the same. You can decide to be horizontally here at that point. Then you've got to divide the sphere into tiny pieces, tiny little cubes, each with some charge rho times the volume of the cube, and that will exert a force like this. And you've got to integrate it over the volume of the sphere, where each portion is at a different distance and different angle. You've got to add it all up. That's why it's a tough problem. So to solve that tough problem, we're now going to use a very powerful trick, and that trick is called Gauss's law. So we're going to learn today about the Gauss's law. Now, a prelude to that, you need a little more mathematical definitions, but they're not bad. I just have to tell you what the definition is. Suppose I have in 3 dimensions a tiny little area, like a snowflake, but it's flat and it's rectangular, let's say. I want to tell you everything about it. I want you to be able to visualize that area. What can I do to specify this little thing? First, I have to tell you how big it is. If it's a tiny area, let its area be dA meters squared. But that doesn't tell me about the orientation of this area, right? Because that area could be like this, it could be like this, it could be tilted in many ways. So if I want to tell you it's an area in a certain plane, what should I do? How do I nail down the plane in which the area is located? Yep.
Define a vector perpendicular to the surface.
Define a vector normal to that surface. Because if you draw that vector, then there's only one plane perpendicular to it. Then we can then form a vector dA, which is a tiny vector, whose direction is perpendicular to its area and whose magnitude is the value of the area itself. So areas can be associated with vectors. You may not have thought about it that way, but you can by this process. Okay? I've told you there's only one ambiguity even now. Do you know what that one ambiguity is? There are two normals you can draw to an area. Right? If you've got an area like this, it can come out towards you or go away from you. Therefore, simply drawing that rectangular patch is not enough to nail that. That's like saying, here is a vector. That's not enough. Where is the head and where is the tail? That's not a vector. That is a vector. Similarly, this area has to be specified some more. And here is what you're supposed to do. You take that area here. I'm just drawing it another place. Draw some arrows that circulate around it in one sense or another. I've picked a particular sense in which they're going around. Then use the famous right-hand rule, where your fingers curl along the arrow and your thumb points in some direction. That is the direction of the area vector. If the arrows were running around the opposite way, then your thumb will point into the blackboard. So an area like this is like a vector without a head. Area like this is a signed area. It's an area got a magnitude and unique direction. Okay, so get used to the notion that a tiny planar area can be represented as a vector. Another way to see that is if you took any area, a rectangular area like this, a square is a special case. If you took two vectors A and B that form the two edges, then A cross B is just double the area. It's the fact that given two vectors, I can find a third vector perpendicular to them up to a sign is what makes a cross product possible only in 3 dimensions. You cannot have a cross product of two vectors in 4 dimensions. Because in 4 dimensions, if I pick two vectors, there'll be 2 other directions perpendicular to that plane. Only in 3D, there's only one direction left. The question is it in or out? That you pick a sign in the cross product. A cross B is something that goes from A to B. Or for an area, you draw arrows around the edge in a certain direction. So area is a vector. So you have to get used to that notion, along with all the other vectors you know. But now I'll tell you why that becomes useful. So we're going to take, let's see. There's a rectangular tube which has got a height h and a width w, and some fluid is flowing along the tube with a velocity v along the length of the tube. You got that? It's like an air duct. Stuff is going through that tube. It's got a rectangular cross-section. Cross-sectional area is hw. If the fluid is going at velocity v along the length of the tube, what is the flow rate? Which is equal to meter cubed of stuff flowing per second. I'm going to denote it by the symbol phi. If I wait 1 second and I watch all the fluid go by me past any cross section, how much stuff goes by? I think you can all see if I wait 1 second, the fluid whose front was here would have advanced to here. And the volume here will be V times 1, because in 1 second it goes a distance V. So the flow rate will be HWV, or area times V. That makes sense? The faster it's going, the more stuff you get. Bigger the cross section, more stuff you get. And this doesn't depend on a rectangular cross section. It can be a cylindrical pipe carrying oil. Again, the flow rate is area times velocity. But I'm going to write this in terms of vectors, because I know the velocity is a vector. But now I have also learned area is a vector, because the area vector here, you can draw a vector perpendicular to this area, and I'll adopt this convention that it's area vectors along this way rather than the other way. Then I can write it as V dot A. Let's check that V dot A is correct. V dot A is the length of V, or the size of V, size of A, and cosine of the angle between them. Here it's got to be very careful. The velocity vector is like this. It's perpendicular to the plane, but don't say it's cosine of 90. The area vector is perpendicular to the area itself. You understand that? When I take the dot product and I ask for the angle between the area vector and the velocity vector, that angle is 0. So for an area, there's a little confusion. The vector representing it happens to be perpendicular to the plane of the area itself. So if you remember that, then V dot A is VA times cosine 0. So this indeed is one way to write the flow. This flow is also called the flux. But now let us do the following. Let's take the same problem and I had this area here. Let me now take a tilted area like this. It also goes from the ceiling to the floor, but it's tilted at an angle theta. So it's a bigger area than the original one. How much bigger? That area prime, I claim, is equal to the base W times this side. This side is h over cosine theta. The theta is the angle between these two planes. It's a bigger area, but you all know that just because it's a bigger area doesn't intercept more fluid per second. Any stuff crossing this guy also crosses this at the same rate. So how am I going to get the same rate? The flux is not going to be V times A prime. It's going to be V times A prime times cosine theta. But theta is the angle between the area vector and the velocity vector, which is the same angle here. So the moral of the story is V dot A prime, or V dot A in general, is the flux or the flow of any vector across an area. If it's a fluid that's flowing, then V dot A is the fluid flow past that area. But you need the dot product, you need the cosine of the angle, because the area, if it's not perpendicular to the flow, is not useful. In fact, you can take a huge area parallel to the flow and nothing goes through it. So area is most effective if the plane of the area is normal to the fluid, or the area vector is parallel to the velocity of the fluid. So that's that lesson. Okay, this had nothing to do with the electric field, but we're going to come to the electric field now. This is just a warm-up. So let's come to the electric field and see what's going on. So I take a charge Q, and I draw the lines coming out of it. How many lines do I get crossing a sphere S? Well, we know that we have agreed to draw 1 over epsilon 0 lines per Coulomb. So if there's Q here, that many lines cross the sphere. I'm now going to relate it to something I can do with the electric field as follows. I'm going to say that if I go to that sphere, I look at the electric field. Electric field is in that direction, E. And any portion of the sphere, I want this where you got to imagine, take a tiny part of the sphere, it's a tiny area, it's got a size dA. What is its direction? Direction of the area vector is radial. You understand? The area is on the surface. The normal to that is a radial vector, which I always denote by ER. The electric field is equal to Q over 4 pi epsilon 0, 1 over R square ER. Therefore, E dot dA is equal to Q over 4 pi epsilon 0, 1 over R square dA times ER dot ER. This is the dot product of the area vector with the electric field vector. The two unit vectors are parallel. The dot product of that guy with itself is just 1. So this is the number of lines crossing the tiny area, because electric field numerically is equal to the line density. So those lines crossing this area, this is the number of lines crossing that patch, which is given by E dot dA. If you add up all the lines, you must add up all the dAs. Sum of all the dAs on a sphere of radius r is just Q over 4 pi epsilon 0 R square times sum of all the dAs on a sphere, that is just 4 pi R square. So you get Q over epsilon 0. In other words, either you can draw the picture and it's immediately obvious to you the lines crossing it is Q over epsilon 0 by construction, or you can remember, hey, the electric field is a direct measure of the number of lines per unit area. The electric field times area times the cosine of the angle between the area and the electric field will count the lines going through a tiny area. If I add them all up, I better get Q over epsilon 0, and indeed you do. So the moral of this little exercise is that the surface integral, this is called the surface integral of the electric field, on a surface is equal to Q over epsilon 0, where this was a sphere. In other words, even if you never heard of field lines, just take the electric field and do the surface integral, you get this. So surface integral is a new concept. You probably have not done that before, and I got to remind you how it is done, at least operationally. If you got a computer, you can find the surface integral of anything as follows. Take the surface over which you're doing an integration, divide it into tiny pieces, each is a little area dA. Take the dot product of the dA with the electric field there and sum over all the patches covering the sphere, then take the limit in which every patch gets vanishingly small. That is called the surface integral of the electric field, and we see that if you do that, you get the charge inside divided by epsilon 0. But that was on a sphere, and the interesting thing was the answer was independent of the radius of the sphere, because the 1 over r square in the field cancel the r square in the area. But it is even better than that, because it's clear to you now without any calculation that if it took some crazy surface like this, the lines crossing that is also the same. Because the lines leave the origin, they go radially outwards, they don't terminate on anything, they're only supposed to terminate on other charges. Therefore, you can count them anywhere you like. You can take a census here, you can take a census there or there, you're always going to get the same number of lines. Therefore, Q over epsilon 0 is also going to be equal to the line count on some weird surface enclosing the charge. So how am I going to count the lines on a weird surface? I take the surface, divide it into little pieces, but now the area vector and the electric field vector may not be parallel because it's not a sphere. But it is still true that if you're trying to count the lines going through, just like in the velocity, you must take the dot product of these two. Therefore, you will again find E dot dA for any surface, any closed surface, is equal to Q over epsilon 0. If you got lost in the mathematics, the physical picture is very clear. If you want to count how many lines leave that charge, you can surround it with any surface you like. If it's a sphere, it's very easy for you to do the check. If it's a crazy surface, it's harder, but they all come from the fact that E dot dA count the number of lines, and that's independent of the surface that's taken. So now that is what's called Gauss's law. So I'm going to write it down here. What I've shown you is the following. Here is some strange closed surface. There's a charge Q inside. Then E dot dA on that surface is equal to Q inside over epsilon 0. This is not yet the theorem, but this is the case for one charge. If the charge were outside, suppose this charge were here, then the lines would go like this, and the total number leaving the surface will actually be 0. You might say, how is that? I see all these lines penetrating the surface, but you got to remember, if I take an area vector here, with the definition for a closed surface, the area vector is the outward pointing normal. For a closed surface, every area has a vector pointing out from the closed surface. Then you can see that in this surface, lines are coming out. On this surface, lines are going in. It's very clear what's going in is coming out because nothing is terminating. Therefore, if you took a surface that did not enclose a charge, this answer would be 0. But if it enclosed a charge, it will be the charge inside, but it won't matter where it is. You can also see that you can move this charge around anywhere you like. You don't change the number coming out, the lines coming out. Then the most important generalization is, if instead of one charge, I had two charges, what do you do? If you had two charges, let us take the total electric field dot dA on a surface. But the total electric field is the electric field due to the first charge on that surface plus the electric field due to the second charge on the surface, thanks to superposition. It's the fact that the electric field is additive over charges. But this one is Q1 over epsilon 0. This is Q2 over epsilon 0. Therefore, we can now write, generalizing to any number, by the way, one draws a double integral with this thing, meaning it's a closed surface. You can also have an open surface. You know, take the skin of an orange and cut it in half. That hemispherical skin is also a surface. But to signify it's a closed surface, we do it like this. On a closed surface of E dot dA is equal to Q enclosed divided by epsilon 0, which means sum of all the Q's. And sometimes we write this as follows. Suppose inside you don't have a discrete set of charges that you can count, but a continuous blob of charge. And the charge has a certain density, rho. It's a charge density. What is the Q enclosed? I claim the answer is you do a volume integral of rho at any point r inside times dx, dy, dz inside that volume. You know, if you want to say how many coulombs are there, well, divide the volume into tiny cubes of size dx, dy, dz. That times the rho of r, meaning rho at x, y, and z, is the charge inside the cube. You add it all up, you get the charge enclosed in that funny shaped object. So this is the final form of Gauss's law that we're going to use. I'm going to use the symbol, which is very useful. This is the theorem of Gauss. And S equals dV. dV is the boundary of S, of V. Now, in other words, if V is like a potato, the skin of the potato is dV. Therefore, if the potato is full of charge, it will emit some electric flux, and the surface integral of the electric flux over the skin of the potato is the charge enclosed inside it. Charge enclosed inside it is not simply some constant density times volume. If the charge density varies from point to point, in each neighborhood inside that volume, you take a tiny section, a tiny little cube of size dx, dy, dz, see how much is in there as a function of x, y, and z, and you do the integral over the volume. Now, these integrals may be hard to do, but you should know at least what I'm saying. This is just a way of counting the total charge inside a volume, and the charge is continuously distributed. So I'm going to show you one application of this, and we'll come back to more next time. And the one application I'm going to show you is to find the electric field due to a solid ball of charge. So I'm going to use Gauss's theorem to do that. This is true for any surface you pick. Doesn't matter what surface you pick. So if I want to find the electric field here, I'm going to pick a surface of radius little r. Let the sphere have a radius big R. I want to find the field here. And I'm going to use Gauss's law. So on the left-hand side and the right-hand side are two different things. On the right-hand side, what is the charge enclosed in that region? Well, the charge enclosed is just some number q. This whole thing is q. That's q spread over a sphere of radius r. Over epsilon 0, that's going to be the surface integral of the electric field on that sphere. E dot dA on that sphere. Now, normally, if you knew the value of an integral over a region, you cannot deduce anything about the integrand. Unless what? There's one exception where if you know the integral of a function, you can find the integrand. You know when that might be? When here's a function. I tell you it's integral from here to here, but I don't show you the picture. What's the integrand? You don't know. But if I also tell you the function is a constant, then I tell you the integral, and you know the width of this region, you can find the integrand. So you're going to cook this up so that this whole integral is a constant times the area of integration. And we argue that if you got a spherical charge density, the electric field must be radial everywhere. You've not proven this, but you argue that because it's the only distribution with lines coming out everywhere, invariant under every possible rotation of the sphere. Because if you rotate the sphere, I won't know you rotated it. So the field pattern cannot look different. If the field pattern looked different when you rotated it, then you have a problem because the cause looks the same, but the effect looks different. That's not allowed. The only allowed thing is a radially outgoing electric field. Therefore, the electric field is radial and also constant throughout the sphere because all points on the sphere are equivalent. There's no reason why this is any better than that. Sphere looks the same from all directions. Therefore, this whole integral is going to be 4 pi r squared times the electric field at that radius r. Because the area vector and the electric field vector are both parallel. So in this dot product, forget the dot product, just E times dA. There's no cos theta, it's just 1. You can pull the E out of the integral because E is constant in magnitude on the sphere. And the integral of the dA is just 4 pi r squared. Therefore, you deduce ER is Q over 4 pi epsilon 0 R squared. It's a very profound result. It looks very simple, but it is true for not a point charge, but for a spherical distribution of charge. That the field goes like that of a point charge sitting at the origin is a consequence of Gauss's law. If the charge inside was not uniform, suppose it had charge Q, but there is more stuff here, less stuff here, this theorem would still be true up to this point. But you can never deduce that E is a constant on a sphere. Because even though the sphere is nice and symmetrical, the charge distribution is not. E could be big here, E could be small here. You know something about the integral over a surface of a varying function. Then Gauss's law is no good. Not useful. True, but not useful. Gauss's law is useful only when, in a given problem, there's only one number you don't know. That number here happens to be, what's the strength of E at a radius r? I know its direction is radial. I know its magnitude is constant on the sphere by symmetry, but what is the number? You can trade that one number for this one number on the left-hand side, Q over epsilon 0. You can calculate it. So I'll come back and do more examples for you guys next time.